Thanks for the introduction. Though I didn't fully understand, but I guess what's the meaning. So good afternoon, everyone. Thanks for the conference. Thanks the conference organizer for inviting me here to give an introduction to our research. So my name is Tian. I'm the chief scientist of computer vision in Noya's Arc Lab of Huawei, and my talk today is titled Exploring the Frontier of Computer Vision in an Era of Big Computing Power and Big Data. Here is my talk outline. First, I'd like to give a brief introduction to Huawei and Noya's Arc Lab. Then I will discuss computer vision research, our research direction and vision, and Noya Arc Lab, and show some recent research progress by some sample research work. And finally, some introduction for AI application in Huawei phone. So first, I'll give a brief introduction of Huawei. So Huawei right now has over 180,000 employees worldwide. Among them, 80,000 are R&D related. And Huawei has a business running in over 170 countries and districts. It has 14 research centers worldwide. In the Intel brand list, top 100 brands, Huawei is ranked number 70, and in the global Fortune 500, Huawei is ranked number 72. And the bottom left figure shows the revenue of Huawei for the past several years, and you can see the sales revenue is increasing steadily for the past several years. And in the year of 2018, the revenue reaches $108.5 billion. So as Huawei's AI research center, Noya's Arc Lab focuses on AI research. And in Noya Lab, we have 6 major directions, six research groups. And the first is computer vision. Second is decision making and reasoning. Natural language processing, search and recommendation, human-computer interaction, and AI zero, focused on machine learning. And our lab supports product departments such as network intelligence, second is enterprise intelligence, and terminal intelligence, and other emerging business such as autonomous driving. And through various channels, Noya Arc Lab is collaborating with researchers over 10 countries, 25 universities, over 1,000 researchers on 50 or more projects. So such programs such as HERP program, Huawei Innovative Research Program, some others like through Professional Advisory Committee, open sources, or investing on startup companies. So it's Noya's vision that in the AI-first era, Noya Arc Lab aims to build a world top AI lab to help the strategic transformation of Huawei AI business with world-class output. And Noya's Arc Lab is headquartered in Shenzhen, China. And in China, we have offices also in Hong Kong, Beijing, Shanghai, and Xi'an. And in the overseas, in Europe, we have offices in London, Paris, and Moscow. And in Canada, offices in Toronto, Montreal, Edmonton, and also we have a small office in Silicon Valley in the US. Now to talk about computer vision research in the Noya Arc Lab. We know computer vision has 3 bases: algorithm, data, and computing power. The fundamental techniques of computer vision include such as detection, recognition, classification, retrieval, tracking, segmentation, enhancement, reconstruction, and data generation, etc. And in our computer vision lab or CV lab, we conduct basic research, and we also have 3 major projects. For basic research, we listed these 6 research areas, starting from the low-level vision, semantic understanding, 3D vision, data generation, visual computing, and finally the vision and multimodal fusion. I'm going to introduce them in more detail in later slides. For the projects, we have 3 major projects. The first one is terminal vision, mainly related to the terminal devices such as phone, big screen, but one of the major output is for the Huawei phone. For photo quality, it's an improvement. So some tasks such as denoising, inpainting, or digital entertainment, or some cinematograph, like special effects for the photo generation. Our second project is cognitive IOV. IOV is the Internet of Vehicles. Mainly it's for the autonomous driving. And our task is for the visual perception and multi-sensor fusion. Our third project in our CV lab is GTS Brain. GTS Brain aims to improve the operational efficiency and effectiveness of the company. And some of the tasks include OCR, 3D reconstruction, and small object detection, etc. Also, the lab, the CV lab, trying to improve the reputation of our Loyal X lab and have a broad impact to the community through the following ways. The first one is AI competition, that organize AI challenges in the top conferences or other venues. Second one is academic achievements by publishing high-quality conference and research papers and have more high-quality patents. The last one is for the talent cultivation. It means how to best educate our employees and intern students. Next, I'm going to give a more detailed introduction to computer vision research in the Loya's Arc Lab. So as I mentioned earlier, computer vision research in the lab, we have 6 areas. So the first one is low-level vision, and the second one is semantic understanding. We consider this is like a traditional 2D vision. And also we see a trend of research shift from a 2D vision to 3D vision. And we consider this is for the algorithm development. And on the data side, in many application scenarios, like autonomous driving, we lack the training data. So data generation or augmented data is very important. So therefore, data generation, next arrow, and visual computing. We're trying to seek the help of the big computing power of Huawei platform. And some of our recent research topics focus on the neural architecture search and network model compression and acceleration. And the last one is vision and multimodal fusion. So first, for the first arrow, low-level vision aims for the Huawei phone and for the target mainly for the photo quality improvement. And low resolution and noise are important factors affecting image quality. Super resolution and denoising can effectively improve the user experience. These are some examples of high-quality images and blurred images and noisy images. So some challenges here. The first is difficult to estimate the statistical properties of noise in the sRGB domain. So sRGB stands for the standard RGB, mainly for display or printing purpose. When image is captured between the raw data and the sRGB, the image has gone through a number of ISP transformations. And these transformations some of the nonlinear transformations. So therefore, it's very difficult to recover the original image and the noise. So that's first challenging. Second challenging is the gap between real-world degradation and the training samples due to different degrees of blur and different degrees of noises. So the third challenging for low-level vision is the limitation of prior information for super resolution from the degraded images. Here, the degraded images are generated by downsampling the original ground truth images. When we say the prior information, it does not mean we do not have ground truth images. It just means we do not really know the degradation model. So second area is semantic understanding. Semantic understanding of images and videos are very important research topics. It has important application in projects such as safe city, terminal vision. And also there are some challenges. So the first challenging is large inter-class differences. For this example, this action hugging, the same action, but the visual experience is very big, is very large. We call the large intra-class differences. And second challenge is small inter-class differences. So look at these two, if you just look at these two standing men, it's very difficult to distinguish their action. But if we put them in the original image, and you can see this one probably is for the conversational talk, and this man is in the queuing, probably queuing for the toilet. They are different, it belongs to different actions, but they have a small interclass difference. The third challenge is the difficulty to distinguish normal and abnormal events. There is a blurring boundary sometimes. For example, for this one, there's a group of people running, and that's a normal event. And this is a group of people fighting, that's a riot, that's abnormal event. So our third area is 3D vision. We believe the analysis of 3D images and videos is the future of computer vision, because compared to 2D data, 3D data contains more valuable information. Here are some examples of medical images of different modalities, such as CT, MRI, ultrasound images, and various video data. So the challenges here, the first one is when we annotating the medical images, it needs professional knowledge. Even in the big data era, obtaining the medical image with accurate annotation is difficult and sometimes very expensive. So that's first challenge. Second challenge is it's very difficult to distinguish abnormal examples from the normal samples in the medical images, because sometimes organ lesion is reflected in the fine details. And third challenge is there are a lot redundant information in video data. So how to mine the useful information and remove the redundancy is very important, also very challenging. And the last challenge is understanding of image and videos largely depends on the detection and the tracking of important objects in the image or videos. And it's difficult to detect and track objects very accurately. So our fourth research area is data generation, because image and video are the basis of tasks such as autonomous driving and face recognition. So therefore, rich data is a guarantee and a cornerstone of vision research. Here are some examples of the face generation for face recognition, and this is person generation based on poses for the applications such as person re-identification for the safe city projects, and that's the street view. That's a generated street view, not the authentic, not the real world. Street view generation for the autonomous driving, for the data, for the model training. Also, there are some challenges here. The first one is manually labeling face, the key points, for example, is difficult and expensive. And second, in this person generation for person identification, personal ID, and the quality of the generated images and videos sometimes, usually is very poor. And the third challenge is in the street view, this data generation, there is a problem called homogeneity problem. For this generated data, problem is very serious. And also the diversity of the generated data needs to be improved. And the last challenge is the high computational complexity of the algorithm is another important factor restricting the data generation, especially for the video data generation. The fifth research area is visual computing. Visual computing is very important for the application right now in deep learning, this area for deep learning algorithms. Some hot topics now, such as network model expression and acceleration, are of great importance to the deployment on edge devices, like a phone, like a camera, like a big screen. And the second is neural network architecture design is a key factor in the performance of vision research. So here, challenging number one is due to the independence of edge computing algorithms, there lacks of a unified platform for edge computing, and it is very inconvenient for users to use. So a unified platform is preferred. Second, currently, the network compression and acceleration algorithm is mainly for the tasks of image classification. There are lacks of a network compression and acceleration algorithm for other specific vision tasks, such as detection and segmentation. And the third challenge is manually design network architecture is labor. So first is needs a lot of professional experience and is labor consuming, labor expensive, and also meets the bottleneck. So neural architecture search is a way. Also due to the lack of the big computing power. So the current network architecture search still needs to be further improved considering performance and search efficiency. Our last research area is vision and multimodals. So the data in the real world are multimodal. Therefore, multimodal machine learning aims to build models that can process and relate information from multiple modalities. Here are some examples. The first one is we have two modalities. One is natural image input from the cameras. Second is this is from the laser. This point cloud. And second one is how to generate the text descriptions for image and videos. We call it image video captioning. That modality from the image and video to text domain. Also, last one is visual questioning and answering. So the challenge here, number one is it is hard to represent and summarize multimodal data in a similar format. We call this is a heterogeneity issue. And the second challenge is it's difficult to fuse information from two or more modalities, and that's data fusion. For example, like natural images with LiDAR point cloud, two different modalities. And the third challenge is it is difficult to identify the relations between sub-elements from different modalities. For example, if you prepare, if you do a cooking following this menu, it's difficult to align the steps in the menu and the actions in the video. That means an alignment issue. And the fourth challenge is when we translate data from one modality to another, for example, in this image-video description, from the image-video content to text domain, the evaluation metric sometimes is subjective and uncertain. And the last one is if we train a model on one modality, with knowledge learned from other modalities, especially on one modality with lack of training data. We can seek help from other modalities. So this is a problem of co-learning. So this basically summarizes the 6 research areas currently in my computer vision group and Noya ArcSnap. Now, next, I'm going to show you some research progress of our group for the past, this is work just done in the past 1 or 2 months. Due to the time limit, here I select 5 research samples to discuss. So they are the first, neural architecture search. Second is object detection. Third, person identification. The fourth, network model compression. And the last one, 3D object detection. Before I go to the details, let's give you a brief summary. So for neural architecture search, we propose a new scheme which can give more accurate, more stable, and faster these results existing the state-of-art last method. And the second, for object detection, we have a new scheme we call the CenterNet, which can generate lower false positive with higher accuracy. It's so far the best result for one-stage detector for object detection. And the third one is for the person identification. We propose faster to deploy new ReID systems, which release the burden of annotating large data sets. And for the model compression, we propose a data-free model compression framework. And that's for 3D object detection. We propose a plug-and-play iterative refinement to improve the generation ability of this 3D object detection. So first, for our recent work on LAS, LAS stands for Neural Architecture Search. And right now, automatic search of neural architecture is going to be a future direction. And so far, the searched architecture has surpassed best manually designs on CIFAR-10. If you are familiar with image classification, CIFAR-10 is like a data set for image classification. However, there also exists a problem. So the problem is a depth map between the search and the evaluation networks. The searched architecture usually are shallow. They have a small number of the layers or cells. But the depth in the evaluation network is larger. For example, in a DATS model, in a search network, it has 8 cells, but in the evaluation, it has 20 cells. So another solution is if we directly increase the network search depth, it's going to be results 2 problems. So the first one is a computational explosion. It is hard to search. Second one results a very unstable search process, and this is usually caused by the skip connection. So our proposed solution is basically 2 keywords. First one is search space approximation, and second is search space regularization. The figure on the right shows a figure for this illustration purpose from input to the output for this normal cell as enlarged on the right. So we have these nodes labeled 0, 1, 2, 3. That stands for possibly for the feature response map. And those color connections between each node, that are the operations such as pooling, convolution, and skip connection. So our goal is to try to learn the weights for these connections so that those operations with higher weights are kept. The operations with lower weights are discarded. In this way, we actually narrow the search space. These are some results. For this search space approximation, in terms of the search accuracy gain, this test error, test error lower is better. So if we search on CIFAR 10, this data set for classification, and also test on search on CIFAR 10, and also test on CIFAR 10, our result is 2.55 compared to the DATS 2.83. And if we search on CIFAR 100 and also test on CIFAR 100, our result is 16.52%, while DATS is 17.54. Here, DATS model cannot get good search results on the CIFAR 10, on CIFAR 100. So it used the search the architecture on CIFAR 10 and transferred or tested on CIFAR 100. And the last, on ImageNet, our result is 24.5 for top 1 error and 8.4 for top 5 error compared to DATS 26.9 or 9% for top 5. And you can see our result is better than this state-of-the-art DATS model. This is performance. Second is search cost reduction. So when we search on CIFAR 10, it takes 0.3 GPU days. If we compare to Google's last year model, it's called MobileNet, and it's generic generic algorithm based, and it takes 3,150 GPU days with the same accuracy. Then if we compare to the recent DATS, it takes 4 GPU days, and our performance is better. And the top figure shows the search architecture. Left is the DATS model. It shows the connection between input and output and the nodes. And there's no connection between nodes between. This is our search results. So besides the input-output connection, there are also connections between nodes. This is equivalent to say we increase the search depths. And through regularization, regularization means in order to keep the search process stable, and we do operations, some dropout for the skip connection, and also for the search architecture, we only keep a limited number of the skip connections. So as a result, it increases the search stability. Shows on this table. So this is the test error before. So the average of error is 2.79, and after regularization, it reduced to 2.65. And for the standard deviation from 0.16, reduced to 0.05. So it means search stability is increased. So our second project recently done is object detection. So the research background is currently the key point-based approach is a one-stage detector, which directly detects an object using a pair of corners, like this scanning person. Okay, you detect a pair of corners, and the combination of these two corners now generates the bounding box. However, in this way, it is unable to perceive the internal information of the objects, which generates many incorrect bounding boxes. For example, this is bounding boxes with correct bounding boxes, but with the previous way, it generates many incorrect false positives. So our solution is we're trying to use the center key points to filter out the incorrect bounding boxes. So because the bounding boxes are generated by the combination of the detected corners. So for each bounding box, we have a center region. We can detect whether this center region contains the detected center points or not. If the center region contains the center points, that means the probability for this bounding box to be correct is high. Otherwise, it's low. Okay. So for example, for this horse, there are two bounding boxes. One is this one, this green one. Another is a big bounding box. And the big bounding box center region is here. Okay, it does not contain the center points of the object. So therefore, it's a false positive. So also for the bounding box here. So after filter out this false positive, that's our results. So for experimental results, on the challenging MS COCO dataset, our method is called CenterNet achieves AP, the average precision, of 47%, which outperforms all the existing one-stage detector by at least 4.9%. So if you do like the object detection, you should know like even 1% increase is very difficult, and we increased this by 4.9 this point in performance. Also compared with all other one-stage or two-stage detectors, except for the latest this corner net one-stage state-of-art one-stage detector, our CenterNet has no pre-training. No pre-training means no pre-trained on ImageNet, and starts from scratch, and others need pre-training on ImageNet. So therefore, our method is more flexible for application. And the bottom figure shows the comparison with the CornerNet, the state-of-art one-stage detector with the CenterNet. And you can see these are the results for the CenterNet, the many false positives. And this is the result of our CenterNet of ours. Many false positives are removed. Also, so for let me say one more. Okay. So let me say one more word is for this object detection and NAS, we also have our software open sources. We put on the GitHub. It's open to the source code, and the source code are open sourced. And so for the object detection, now it has in 2 to 3 weeks we got over 600, 700 stars for this work. And so the third work is a single camera training for Real ID. That's for the person identification. Let me hold on a second. It's too. All right. I'm getting excited. Okay. So single camera training for Real ID. Sorry. Okay, this is for the application of a person identification. So person identification means you search the same individuals from a large amount of the images captured by surveillance cameras, like this figure shows. The problem of Real ID, usually a large problem is annotating training data set is very time-consuming and expensive, especially you want to annotate a person across different cameras, because when a person is captured by different cameras, they have captured by different viewpoints, different angles, maybe different lighting conditions. So annotating the same person across cameras is going to be sometimes difficult. So our idea, sorry, I pressed the wrong button. Okay, this is you annotate each person across different cameras. That's more difficult. So we propose to just investigate the single camera training setting. We call it SCT. Means we only annotate one person under one camera. Because when a person is captured by one camera, we can use the object detection and tracking easily to track, to label the person. And this is for annotation, the cost is very minimal. And experimental results, we tested on 2 benchmark data sets. The first one is the Duke Real ID data set. And the rank 1 accuracy, ours is 66.4. So compared to the state-of-art unsupervised method published in ECCV 2018, ours has nearly 20% of improvement. And second, when we test on market 1501 dataset, the rank 1 accuracy is 65.8. So the take-home message is, under this single camera training, SCT, it alleviates the burden of data annotation and greatly accelerates the fast deployment of real ID systems in the real scenario. So our fourth research is called data-free compression. It's for the network compression. Because when we want to run large models on mobile devices, it's difficult. So therefore, efficient CNNs are urgently demanded. And existing network compression algorithm obtained promising results. It can achieve the same accuracy, but achieve several times of compression ratio. However, the problem is most compression, this algorithm cannot be launched without the original training data set. However, in practice, in many cases, this original training data set is unavailable due to the, for example, privacy, law restriction, or data transmission issues. So we propose a method, we propose a GAN-based approach to generate training images. So for GAN-based approach, it needs a discriminator and a generator. For generator, we design loss function to generate images. And we train the model with generated images and use this stealing for model compression. And for the discriminator, we use network to be compressed to build. So results, with a nearly phi architecture, we will achieve 98.2 accuracy on meanest dataset without the training dataset. It outperforms all state-of-the-art methods by 6% at least. And this result is even closer to the 98.93 that use the original dataset. Ours don't have an original training dataset, it's by generation. Sometimes when we do not have the original training dataset, we use the replacement. We use the alternative dataset as a replacement. For example, CIFAR 10 and CIFAR 100, they have a large overlap. So they serve as a replacement alternative dataset for each other. So if we train on CIFAR 100 and test on CIFAR 10, the model achieved 90.65 in this accuracy. And ours, without the original training data, is 92.22. And if we train on CIFAR 10 and test on CIFAR 100, the model achieved 69.88, and ours, again, without the original training data set, is 74.47, and nearly has a 4.59 this point increase. So the message is, with this data-free compression method, the generated images achieve very similar performance with the original data, and even outperform the alternative dataset replacement. Our next project is maybe this is the last one. Okay, a molecular 3D object detection. And existing method using tight constraints or depth estimation to locate images, to locate objects in a 3D space. However, some problems are it's difficult to achieve large 3D IOU. IOU is evaluation metric intersection over union. And for distant objects, a tiny displacement in the 2D space can usually lead to a large shift in the 3D space. So our idea is by deep reinforcement learning method, we propose reinforced actual refinement network to iteratively refine the 3D bounding box. So for example, in this figure on the right, step 1, that's the initial 3D detection results, and the IOU is no, 0.22. And then we just find the principal actual direction, and then we move the bounding box in all possible directions and different step size. Then we use RL, reinforcement learning method, to optimize it. And so that's step 15, IOU increased to 0.95. And the results on the kitty bird's eye view evaluation and 3D object detection evaluation, our method gains a 6-point improvement compared to the this mono 3D and deep 3D box method, surpassing all the state of art. And these are some qualitative examples. So the first two rows are the before refinement and after refinement. So before refinement, for example, IOU from 0.14 to 0.71, 0.31 to 0.64. Okay, and the last two rows shows refinement path from left to right, from top to bottom. You can see this is the network can learn a good moving policy. The IOU is steadily increasing from initially 0.27 to last this 0.75. This is some visual examples. So for this, I think the take-home message is we propose a plug-and-play iterative refinement method that achieves a significant increase in performance, but with a minimal time cost. Of course, due to that time limitation, we have more recent research progress on the age estimation, facial expression recognition, self-supervised learning, solve the image puzzle problem, GAN model compression, unified cost-to-fun framework for detection, segmentation, and classification. And the last one is the fusion of vision and NLP. For example, giving a text query how to locate a video content in the videos. Okay. So last, to show some of the AI application in Huawei phone. These are some projects done in our terminal vision projects, and I discussed it earlier, terminal vision. And this shows some examples. You can see the image and video quality can be significantly improved with AI. Some examples on the top left, image video enhancement and original and ours shows the better color balance. For example, the sky is become more blue, the trees are more green. And this is semantic fine segmentation. It can achieve the hair level, like semantic segmentation. And that's for the super resolution, text super resolution, and face super resolution, original and ours. And also for the image semantic summary, like image video description, image video captioning, and some results are passed in a pocket note. Finally, let's automatically detect a person, focus a person, and track the person during this performance. Another is using AI to realize intelligent perception of things and making mobile phone become assistant in life. This shows the perception and understanding of mobile resources, such as the phone and users before and after the photo taking. Okay, before the photo taking, understand the mobile resources. For example, understand how much computing power is left in your phone. This is intelligent resource management. And after, understand the user behavior. This is serve as an intelligent assistant. And during the photo taking, it can recognize the things, recognize the objects, so that you can optimize the hyperparameters for the network. So far we can recognize 500 scene recognitions. I can recognize over 1,000 objects. Okay. So finally, as a conclusion, and so our research, I guess, basically is based on the big computing and big data platform. So Huawei announced a series AI chips. It's called Ascent, Ascent Max, Ascent Milli, Tian, Night, like Nano, and so on. And so Huawei AI chips can support this frontier research. And we have 6 research areas from nodal vision, semantic understanding, 3D vision, data generation, visual computing, and vision and multimodality fusions. Many research work are still ongoing. Hopefully, we will generate more results and report to you next in future meetings. And above the fundamental research, we're trying to achieve some commercial values through the projects such as medical image diagnosis, medical systems, security, safe city projects, and digital entertainment for the phones, and some applications in autonomous driving. So that's the talk of mine. Thank you for your attention.
И у нас есть время буквально на пару вопросов перед следующим спикером. Ваши руки. Ага.
Thank you for a good overview. I want to ask about your technological stack. What kind of deep learning framework do you use for research or production purposes?
For which platform? You talk, I didn't get the question. Which platform are you asking?
What kind of deep learning frameworks
I see.
do you use for production and research?
Because we have over 50 intern students. Most of them use PyTorch, some of TensorFlow. And Huawei is also developing its own, like TensorFlow, like PyTorch. It's called MindSpore. And the students mainly use PyTorch, but they use many kinds of this available frameworks. Okay.
Hello. Thank you for a nice presentation. I would like to ask you if semantic fine segmentation will be available open source. It would be nice to integrate that into GIMP.
Which one?
Semantic fine segmentation, like the thing that extracted background from person, yes, like fine segmentation.
Whether this open resource?
Yes.
I don't think so.
Also,
certainly, I think we have this done in our terminal vision projects. And I also believe probably if you search on the internet, probably some are available, but I'm not sure.
okay, thank you.
But the first work on NAS, neural architecture and object detection, we already made it public available.
Okay, thank you. And also, what license is used in CentralNet? What license is used? It is open source, but what license?
What license? I'm not quite sure. So this is what license? Do you know?
MIT, GPL.
Oh, I see. I'm not quite sure, but the student, we just made it public available. And if you search the CentralNet on GitHub, you may find it.
Okay.
Thank you very much for your very interesting presentation. Tell us, please, in your CentralNet implementation for object detection, in your CentralNet.
CentralNet, yeah.
CentralNet, yeah. You use such a simple approach with a center landmark. So what about heat map regression, which is widely used in, say, pose estimation tasks? Did you committed some research into that direction? So how did you come to that CentralNet approach? So tell us, please.
Actually, CentralNet approach is sounds like a very simple but very effective way, right? And so that's why we are surprised to know it gets so good results. So recently, researchers from UC Berkeley and UT Austin proposed some very similar work, even with the same name, CentralNet. And I think this is from the previous state-of-the-art method coordinate.
How many stars on the GitHub they have?
I don't know. We compared the performance. So our performance is probably 1.5 or to 2 points better than theirs. So
Okay.
made it quickly publicly available on GitHub.
Okay, thank you so much.